Hi, I'm Kim Haynes, a product marketing manager in the Chemistry Technology Center at Waters Corporation. In part 2 of this series, we will look at the 5 big challenges to overcome when designing a successful sample cleanup and enrichment protocol for peptides. These are protein binding, non-specific binding, peptide solubility, peptide specificity, and recovery. I'd like to discuss each of these briefly, and you can refer to the bioanalysis sample preparation and method development cards for more details. The first consideration is protein binding. You have to take steps to prepare the sample and eliminate binding of the peptide to proteins or other matrix components. If you do not, the peptides will stay bound to the proteins and pass right through the solid phase extraction sorbent due to size exclusion effects. There are some tricks you can use to do this, and it really depends on how strongly the peptides are bound to the proteins. You can start with something as simple as diluting the plasma 1:1 with a 4% phosphoric acid solution or a 5% ammonium hydroxide solution, but more aggressive steps may be necessary. For example, denaturation with guanidine hydrochloride, urea, or SDS. You may even need to do a protein precipitation in a 1:1 ratio with acetonitrile, but don't go any higher, or you may precipitate your peptides right along with the proteins. The next consideration is a tricky one, non-specific binding. Peptides are notoriously sticky and will stick to glass and other surfaces. This leads to low recoveries, high variability due to absorption losses at different rates, and high detection limits. To overcome this challenge, there are a few things you can do. Avoid using glass for sample preparation or storage in the autosampler. Use polypropylene or materials designed for low binding of peptides and proteins. During the sample cleanup and enrichment in solid phase extraction, use the microelution format. This allows you to skip the dry down and reconstitution step, since the elution volume is only 25 to 50 microliters. Many peptides can be lost in the dry down step due to absorption onto the collection container or failure to resolubilize. The bonus is that the microelution format allows up to a 15-time increase in concentration, enabling the lower detection limits that are often necessary in these assays. When preparing stock solutions, make them in a high concentration to mitigate losses and saturate the surfaces, then do subsequent serial dilutions. You can use things like organic solvents, detergents, and carrier proteins to your advantage. Use organic solvents or detergents like SDS or guanidine hydrochloride to promote peptide solubility. Finally, you can add carrier proteins to solutions that have low protein concentrations, such as neat solutions or cerebral spinal fluid. This saturates the binding sites of the surfaces that the sample may come into contact with and therefore prevents absorption losses. 5% rat plasma, or a 40 microgram per ml solution of BSA, works well for this purpose. The third challenge is one that afflicts chromatography as much as sample preparation, and that is peptide solubility. Those of you that have worked with small molecules in the past may have learned the hard way that peptides behave very differently. From the initial solubilization from powder through the sample preparation and chromatography steps, we suggest limiting the organic concentration to no more than 75%. Otherwise, you risk precipitating your peptides, and that will show up in terms of low recovery in sample preparation and possibly even carryover in your chromatography. You can use modifiers to promote solubility, but it may require higher concentrations than what you have used with small molecules. Examples that have worked include a range from 1% up to 10% acid or base, such as TFA, formic acid, acetic acid, or ammonium hydroxide. The fourth challenge is specificity. Let me explain. In peptide bioanalysis, we need to create highly sensitive and reproducible assays. In many cases, protein precipitation, while very popular with small molecule bioanalysis, will just not be good enough for peptides. Protein precipitation uses high concentrations of organic solvent, which can result in peptide precipitation losses, right along with the proteins. In addition, protein precipitation does not remove any other matrix interferences, which can ultimately lead to matrix effects. Protein precipitation typically requires a dry down and reconstitution step, which again can lead to peptide losses due to absorption to the container or failure to resolubilize the peptide. The specificity I refer to here is gained by creating a sample preparation method that uses orthogonal cleanup approaches. both reverse phase and ion exchange to selectively capture your target peptide, while allowing you to wash away the unwanted matrix interferences. Then, you can concentrate your peptide in a small elution volume that can be diluted with a little water and directly injected into the LC-MS system. The last challenge is low recovery. In reality, low recoveries, or variable recoveries, are usually just a symptom of one of the 4 problems I just discussed previously. When you have low recoveries, think about the steps you can take to reduce protein binding, nonspecific binding, peptide solubility, or increase peptide specificity in your sample cleanup protocol. There are also some steps you can take to make sure that you're using your sample preparation device properly, and you can learn more about those in the troubleshooting section of this guide. We really hope this module helped shed some light on the 5 big challenges to overcome when designing a successful sample cleanup and enrichment protocol for peptides. For more information about this and other related topics, you can always visit the Bioanalysis Bootcamp to learn more and increase your peptide and protein quantification fitness. Thank you.